This content is brought to you by BEC Financial Technologies, developing and operating IT for Danish banks.
James Livingston is a solution architect from TPConnects, and he is leading technical team through extremely complex integration in the travel industry. Warm welcome for James.
Thanks. My name's James, and at TPConnects, while I'm an architect, I'm quite involved with a bunch of technical things too, and I lead one of our engineering teams who concentrates on things like performance and security. Performance is really important in the travel industry because there are a lot of interconnected systems across lots of companies that have to work together. What we do in the industry, you don't see as a consumer. We sit between suppliers like airlines and travel agencies, whether they are physical stores or online. So we're a bit hidden away, but what we do is actually quite important. As with the first presentation this morning where everyone's talking about moving from mainframes to microservices, the same is in the travel industry. A lot of what exists was designed in the 70s for mainframes, so very big monoliths. And the whole industry is trying to move to microservices where all of these companies can work together, and that has a lot of challenges. Performance is one of them. So what is the reason performance is important to us is we have a high API call volume. So we have millions of API calls a day, and the whole industry itself has probably hundreds of billions of API calls a day. We're trying to move to a microservice architecture, and it's quite latency sensitive. So if you imagine you want to buy a flight to London and you go onto a website and search for a flight, if it takes 30 seconds to show you the results, you're going to close the website and go somewhere else. So people care about how fast it is as well. Traffic varies a lot across the day. At 2 a.m, you don't get many people searching for flights. And it also changes across the week and changes across the year. And cost is also really important because our customers, one of the reasons they want to move to new companies is to save money. And the margins are quite small, so we have to do things cheaply. And trying to make things very fast, very cheap, high volume, all of these are quite difficult to do if you want to do them all together. So part of that is doing testing to understand the performance of your system. And I'm going to talk about a bit about that today and why lots of people get asked to do performance testing and then do a fairly bad job of it. It's that they've been given the wrong thing to do, or in many cases not even explained what actually they need to do. The first place to start is why are you even doing performance testing? The reason any of us do testing is to answer a question about quality. With functional testing, people want to know, does it work? Does it do what it's supposed to do? You can have user experience testing where you figure out if it's easy to use and how do people actually want to do things. And performance testing answers a lot of questions. Is it fast? Does it scale? How many resources do I need to give it? Can I make it cheaper? All of these kind of things are performance testing. And what's really important is that these are not necessarily one kind of performance test. So if you ever get told, just go do a performance test, you need to understand what it is you actually want to test for. So there's lots of different kinds of performance tests. One of them is a microbenchmark. That's where you get one really small thing and try and see how fast it is and can you optimize it. You may get asked, can you handle so many requests a second? That's normally a load test. A stress test is finding out when it breaks. So because it may not be far enough and you may need to handle higher load, it may also just want to know, because to fix things, you need to know what breaks. There's a lot more types and you need to actually understand this. So to performance test a system, you need to know what the system is. Are you testing one microservice? Are you testing a function? Are you testing 50 applications working together? What is it that you actually want to test? And surrounding that, you need to have other systems. You need to have something generate load. Your system may talk to external systems. That happens a lot in travel. So for the most part, we are not the source of truth for anything. We go off to airlines and go and search for flights and then book them. We may go off to hotel companies. We don't do this ourselves. We're just kind of the middleman, so we have these external systems. And a really important question when you're performance testing is what do you do with them? Can you mock them out? In some cases, that's pretty easy. Just get a request, send a fake response back. In other cases, it's actually extremely difficult. So in our area, bookings are one of them. When you do a booking, there's unique identifiers and a lot of data that links together, and that's quite hard to mock out. This is also true of your data stores. If you are doing a certain kind of performance test, you want to use your real database because maybe that's the bottleneck. In other situations, the database or the data store may be something you don't want to test and you kind of mock out the database. And you also need some way of monitoring what's happening. So your load generation tools will give you things like how many requests did it send, what was the average response time, but that doesn't tell you what's wrong. If it performs badly, what do you need to do to fix it? And so you need all of these components to fit together to be able to do your performance test. And a lot of the challenges arise from not having all of these. And if you pick the wrong ones, like you were trying to test one microservice and you actually test your entire system, maybe something else is the problem. For the monitoring, some of you probably have tools like Datadog or New Relic or something your cloud provider provides. These type of tools are really good because they can tell you what is actually taking up the time, what is the bottleneck. If you don't have those, Java has some built in, so the Java Flight Recorder, JVisual VM, those tools are quite helpful for analysing that too. So what I'm going to show you now is some charts that were sent to me in an email a couple of months ago by someone internally going, we've run a performance test, can you tell us if it's good? And the answer is, I don't know. What were you testing? And was it a good test? So we have a graph of some load and it went up for a bit and I don't know what happened. The latency spiked and then was flat. Is that good? The CPU charts are up and down and all over the place. What does that mean? By itself, this doesn't really tell you anything. So an example of what's wrong with this, this system was having load before we ran the performance test. So whatever this background load is was probably going on during the performance test, which means it's not isolated, which means the data is going to be very noisy and you may see things that are not actually part of your test. The performance test was pretty short, 5 minutes. 5 minutes is not really enough time to do a lot of these performance tests if you're hitting a microservice. Particularly when you're talking about something like the JVM. You put load on it, it does just-in-time compilation of the code, it does a lot of optimizations, and every application, even if it's not Java, caches a field, all these things happen. So by the time it had finished optimizing the code, the performance test was probably finished. So that's why you get that big latency spike at the start, because the application wasn't ready for load. Someone thought it was a good idea to restart the application right before the test, so that way it was all fresh and clean, there was nothing in it. That's actually a problem, because you need the JVM to be warmed up. If you look at the timescales on these charts, they're from different periods of time. These ones over here are from about a 15-minute period. This CPU performance one over here, it's from 3 hours, so most of it's not actually relevant. And the number of requests was 300. We handle millions of API calls a day. What is 300 requests going to tell us? The answer is probably not very much. The biggest problem, though, is that they didn't actually know what they were doing the performance test for. Someone just told them, go do a performance test. And without knowing why you were doing it, you can't know how to set up the test to produce useful information. It's just a whole series of charts that don't actually tell you anything. The most important part of the test is actually planning about what you're doing. So you need to understand the scenario and why someone wants to do this. As an example, let's say our system gets 10 requests a second and sales have come over and go, we're getting a bunch of new customers and they're going to start with us soon and we need to handle 20 requests a second. Can it handle the load? That is a question you can actually then go and do a test for. Obviously, you can already handle 10, you can put more load on it. But there's a few different scenarios. One of them is that we handle the load easily. We don't have any problems at all today, and we think we could handle a lot more with no more servers. It's quite common that you may have a couple of servers for reliability, that if one of them fails, the other two will pick up and there's no issues. If that's the case, and you're not using much of the resources, you can still have 3 servers, and the question is, can those 3 servers handle the load? So, for example, it might be 8 a second per server. Another scenario is you have more servers. You have 5, you have 20, and they're handling the load, but only just. And in that situation, you probably need more servers, or you need more CPU or memory. And so what you want to know is, can those servers scale up in terms of number of resources? Maybe you have a relational database. Maybe you're concerned it could be a bottleneck and you want to check if it is. These are 2 very different scenarios because what you want to do is actually quite different. They're both performance tests, but they're not the same kind of performance test. So I'm going to go for an example of the first one where our system handles the load and we just think we want to handle more load with the same servers. So we need to design the test. So as I says, more transactions a second on the server, that should be easy enough to test, but you need to consider a lot of things. Like I said, you need to warm up the JVM and give it a bit of a test run at low load, so the code's optimized, caches are filled. That way, when you actually start the load test, you don't get all of that stuff at the start showing bad performance because it's only just been restarted. And then you want to slowly increase the load over a period of time up to what you already handle. Hopefully you don't get any problems because that's what production's doing. And then you want to ramp up the load up to where you want to aim for. And what you want to find out is does it handle it? If it breaks, why does it break? And to do this, you need to actually ramp up the load slow enough that you can actually look at the part of the chart where something goes wrong. If you ramp up too quickly, you'll just have one bar in the bar chart and it broke and you can't tell why. And then usually you want to hold it to that load for a longer period of time to make sure it actually handles it over time. Many applications can handle brief spikes of traffic. They have queues internally, they have thread pools that do the work, and a brief spike is fine. But if you have it over a longer period of time, it may not work anymore. So what we have here is an example of a tool called Gatling. It's a load generator. It's an open source one, you can use it for free. And what you do is go write your performance test as Java code. So what we have here, we're just defining one API call, which is one GET request, nothing else. Normally you would have a series of API calls though. So in terms of your API, you're not just doing one thing. You do one thing, then something else, then something else. And we're going to do an open injection test where we have a constant load of 1 request a second to warm it up for 5 minutes. Then we're going to say ramp it up to 4 over 10 minutes, up to 8 over 20 minutes, and then hold it there for another 10 minutes. So it's probably a bit low on the screen for everyone at the back. What's really important here is also the open injection. So there are 2 types of kind of load tests. One is called open and one is called closed. If you have API clients, they tend to be open. If your system slows down, they keep coming. API clients often don't back off if you're struggling. And open just means one request a second, just keep sending them. If you have a closed test, this is more like when you have users in a web user interface. If your system slows down, they sit there and wait for it before they do the next step. So if you're doing closed injection, it's like virtual users who come in, and if your system slows, they also slow. So the way those tests are written is that we have 100 virtual users who do something, think about what they're doing for 30 seconds, then do something else. And if you run this kind of load test, I'm obviously not going to run it here because it'll take 40 minutes, but if you run this kind of load test, the actual output of Gatling tells you a few statistics like the average latency, were there any errors, but that's not the interesting part. The interesting part is what you get from your monitoring system. And you'll get something like this. What you can see in the top left graph is we have that load, so that was our 1 request a second coming in, and then we started ramping up, and then at a certain point the request rate graph started wobbling up and down, and our latency on the bottom left started going up. What that means is the system was starting to struggle. It was handling the load, but it was slowing down, and then a little bit further later, maybe it's another minute in my test, the latency just went up from 3 seconds to 60 seconds and the whole system started timing out. So that's when it broke. So what you need to then go do is zoom in on that bit where it started breaking, just before and just afterwards. And this is why you need to have the load test be long enough that you can zoom into that time period. If your monitoring tool gives you data once a minute, you probably need that period to be 5 or 10 minutes long so that you can go and see what happened. But there's a few things you can just start with to look at. So over on the right-hand side, the heap usage was fairly flat. So it's probably not a garbage collection and memory problem. There's also the GC chart. The thread count did start increasing. That could be the cause, or that could be a symptom. In many cases, it's just a symptom. You start struggling with load, so things are queued up, you have thread pools at scale. That is often not the problem, but sometimes it is, so it's worth noting. And the tool I'm showing screenshots of is Datadog, because we use it, but there's plenty of other tools that do this kind of thing. And then you get to some more interesting ones. CPU usage was increasing from 0.6 to 0.8 of a CPU core. Probably not a problem. It didn't hit 100%. And if we had a system that was auto-scaling, then it would just start up another server. That's probably not a problem. This graphic is interesting though, which is called lock contention. And what this is showing us is there is some lock inside the Java application that is started being heavily contended, and lots of threads are fighting over the lock. And the point when it broke, every thread spent 6 seconds waiting every second. So that is our performance bottleneck here. It's some kind of lock contention. So what you then need to go do is, if you have a tool that does it, go get the information out of it. If you don't have a tool that provides this kind of monitoring for you, what you then need to do is probably reproduce it on someone's laptop using JVisual VM or one of the many other Java profilers to try and go find where the lock is. So the information that it gives us is a bit of a stack trace. On the right, which is not the main problem because it's thinner, if you go click on it, there's actually logging statements. Which is an interesting thing because logging shouldn't show up too much in any kind of lock contention. But it does show up a bit, which is a bit concerning. So it's not our main performance problem, but that's when we need someone to go look at how much is our application logging, because writing to the console and log files shouldn't in theory be a bottleneck. Maybe we're logging too much. Maybe someone's turned on a debug statement in production that they forgot about. The main thing is this XML code. And this particular one, it's actually loading XML transformation factories all the time. The industry standard, the standard in our industry is XML, unfortunately, which is a bit slow. And this particular problem, It's actually the Java XML libraries are scanning the Java classes on every single request. If you just go and Google that problem, there's a solution to it. That was our particular problem here. So we then had to change some code to make sure the XML stuff was cached all the time. We weren't scanning all the classes on every request. So we had to go away and investigate this. An engineer goes and fixes it, and problem solved? Not really. That was our problem. What's the next problem? You solve one problem, and then another performance problem turns up. Maybe rather than breaking at 6 requests a second, it now breaks at 6.5 or 10. There is always a next performance problem. And this is not something that you always have to solve. Something is always going to be the bottleneck. Memory, CPU, locks, the database. There is always some reason why your application can't perform better, and you don't always have to solve it. Sometimes you go, it's good enough, it'll handle the load we need, it doesn't cost too much, it's fine. But sometimes you do need to go and solve it. So it's always important after you make any change to actually go do the same performance test again. The first thing, did you even fix the problem? Maybe whoever's working on the code didn't fix it properly, it's not even fixed. If it is, what is the next problem? We solved that lock thing. Maybe the problem is we have some code using too much CPU. Maybe there's a database query that's not optimized. You need to go and find out what the next problem is and then decide if it's worth solving. Let's just say we're successful, we solved our problem. Do we need to do a different kind of test? So we've now scaled up and we can fix the concurrency bottleneck. Do we need to optimize costs to make it cheaper to run? Is there some other kind of test you want to do next? Performance testing is not just one thing. In some companies, they care a lot about cost. We're one of those because we don't get that much money from our customers, so we need to try and decrease the cost sometimes. But if it costs you fractions of a cent every hour or some tiny amount of money, you probably don't care about cost. And the other thing is, you also change things. The performance test worked this week. In 3 months' time, do you need to do it again? Maybe you've changed the code. Maybe you have a new feature you need to performance test. So you often want to go and repeat the test later on. So it's quite important to make sure you save the data you get. Those monitoring tools, we go and take some screenshots of the interesting parts. If there's any tables, we extract them and put them somewhere. So in 3 months' time, when we go and rerun the test, is it faster? Is it better? If it's not faster, maybe that's okay. Maybe there's a new feature that makes it slower, and that's okay. But you need to be able to compare to the past as well. So that's a bit about testing a whole system. And it's important to be able to do that. But often what you'll find is the code is a problem. You've used the wrong algorithm somewhere, and this thing is an n-squared algorithm where you have too many loops inside of loops. Or maybe you have the wrong kind of list or hash map or something, and it's actually a code level problem in one small area. System testing can identify that, but it won't actually help you fix your code, which leads on to another kind of test, which are microbenchmarks. And microbenchmarks, as the name suggests, are for small things. It's a bit of code, a function, a class. And it's really important to do this kind of one if you want to do optimization of code. And what's really important is the JVM actually makes this really hard. All of that just-in-time code compilation and all of the magic the JVM does to make things perform well actually makes it really hard to do small-scale performance testing. I've got a little bit of a code fragment on the screen. Don't know if you can't see it. It's just a simplified version of something we do. In our flight search responses, there would be lots of repeated data and over again, going Emirates flight 123 flies from here to here at this time to this airport. And so what happens is the responses we get from our partners has data tables in it. So there are the flight results, and it goes, refer to this flight number. Refer to this, what they call fare family, which is the cheap one, the expensive one. There's all these data tables in it. And these have string identifiers, and we need to go and look up things in the data table with these string IDs. So naively, one thing you can do is we have a list of entries in our data table and go and search through for the string IDs. That's not particularly efficient if you have hundreds or thousands of entries and you're doing string matching inside for loops, inside of for loops. Sometimes this is actually fine and the naive approach is okay, but often it's a terrible idea. So one thing we want to do is let's just kind of create an index in memory where we have a map of the string IDs to the actual data. And then it's just a hash map lookup, which should be much faster. Important question though, is it actually faster? I think everyone here would think it's faster, but is it? So what I did is what everyone does, and just write a bit of code. I'm just going to use current time in millis, do it a million times, get the current time in millis again and subtract them. That's how long it took. And I've just gone process the results, just have an empty method. It's easy. And just make a bit of fake data. And what happens is, that's the wrong thing on the slide. So after writing this for this to run, the really dumb approach took 120 milliseconds, and the smart index approach took 500 milliseconds. So the smart thing we did to make it faster made it 4 times slower. Does anyone think that's right? It's probably not. And this is the thing you'll find in performance testing. If the data says something is wrong or something is not an improvement, you need to ask yourself, is it actually not an improvement? Because people are certainly wrong. Or did we just test badly? And often the answer is you just did a bad test. So there's a number of problems with this. Like I said before, the JVM isn't warmed up. And it actually takes some time to warm up, potentially minutes under high load. So what's happened is we've run a performance test that took a fraction of a second. The JVM hasn't optimized any of the code. Even if you ran for a few minutes, it would only have just finished optimizing when you got to the end of the test. So that's one problem. Maybe the code optimizes differently. The other thing is I had some pretty simple data. There's only 3 flight results with 3 combinations of flights. Our real responses have thousands, like 5,000, 10,000 results, and there are hundreds to even 1,000 flight options. That data is not realistic, and it's very, very small, and probably fits in the CPU cache and things. Real data won't. So our data is not particularly good. And also, the function I wrote to go and just do some work, which our real code does, just empty method, don't do anything. The problem is that changes the JVM optimizations. The JVM is quite smart. It goes, you don't do anything, optimize that function away. You don't actually even use the output that the other function generated inside the for loops. I'll remove that. You have a for loop with nothing in it. I'll remove that. And the JVM, once it optimizes, is actually so smart, it doesn't always happen, but potentially, it replaced this with no code at all because we didn't actually do anything with the answer. And this is a real problem when you're doing these kind of micro benchmarks is you need to account for all the JVM smart optimizations and take into account, but you also need to fight the JVM optimizations because otherwise it may optimize away your whole test program. So you need to convince it, this work we've done is actually important, please keep it. And the solution to this, like a lot of things, is don't do it yourself. There are people that are much smarter than you, that are much smarter than me, that are much smarter than everyone else who've done this for us. So there's a tool called JMH, which is the Java micro benchmark harness. It's written by a very smart guy called Alexei Shiplev. He's worked for people like Sun Microsystems, AWS, Red Hat on Java performance things. And it takes care of all of the messy bits for you. So you don't need to remember to warm up the JVM. You don't need to figure out how to make it not optimize away your code. So the one thing we do need to do ourselves is make some real flight data. So this is a bit better. I've told it to generate 2,000 results, which refer to some random combination of 1 to 10 flights out of 500 in the data array. That's more realistic as to the size of the data, so maybe that will help. It still, however, may not be perfect because every iteration of this test uses exactly the same data. On the other hand, if you actually move this inside the test and inside the for loop, the problem is you are then generating the data on every request, which may not be realistic either. So there's a bit of a trade-off between doing things inside the test, pre-doing them. One thing you may want to do is try both ways and see what difference it makes to the answer. Then the JMH code, you just go @benchmark and write some code that does something, which is just run our other function we wanted to test. So I ran it once with version 1, once with version 2. But the other thing is, what do we do about the JVM optimizing away our code because it doesn't actually do everything? JMH has a thing called a black hole, which, like real black holes, eat everything up. Here, what we do is we tell the black hole to consume the objects that the code was generating and iterated over. The JMH black hole eats them up and forces Java to not optimize that away. When we actually have this code that does the work, it actually takes some time on the CPU as well. So we've told the black hole, don't just consume the objects, also consume CPU time. That will also change the JVM optimizations. I've just picked the number 1 here because it's the smallest number I could tell it to do. And we don't actually do that much work. If you do a lot of CPU computations, you may want a bigger number in there. You can just try different numbers. I'm not going to run this test because JMH takes a long time to run it. It will spend several minutes warming up the JVM, several minutes running all of your tests, monitor how it gets optimized over time. And just because maybe there's noise because, I don't know, you're checking your email or doing something else on your laptop, it actually runs the whole thing from scratch with JVM optimization runs 5 times. So we're going to be sitting here 15 minutes, just things scrolling past on the console. But what happened is without our index, with consuming 1 CPU unit, whatever it decides that is, we got 144 operations a second. And with the index, 7,059 operations a second. So in this case, it seems like it actually helped. And this seems like a more realistic number than what we got before, where it was several times slower. That said, this is just a number. It's a more realistic number, I think, but is it correct? Still don't really know the answer to that, so might need to do it a few times with different result set sizes, maybe different fake CPU amounts of work and just see what it does. I'm not going to talk about today. If you really care about low-level optimization, you can tell JMH to monitor how the JVM optimizes your code to machine-level instructions to actually see how the JVM is optimizing it. Most people here, including myself, won't do that. JMH is actually written for people who work on the JVM itself and they care about it. It's there if you want to look at it. It's interesting, but it's probably not something that you'll go and do yourself. So this is a bit of a test, but as I said, these are just numbers. You need to try a few different things, different variations, and see if the numbers are consistent, because maybe our fake data just did something wrong. And that's the most important thing with performance testing is, aside from the planning, analysing the data. You get numbers, but what do they mean? Are they telling you where there's a bottleneck? Are they telling you that everything's actually fine? If you handle 10 requests a second in production, Do you care the difference between 100 and 110 as what you can handle? Probably not. It's 10 times what you have. So maybe it's a problem for later. Because optimizing your programs, the start is very easy. You can just fix some simple things. Then it starts getting really, really hard. And you have to really ask yourself, is it worth it? In many cases, the answer is no. Just because you can optimize something, you don't have to. Is it worth spending a month of your time making your code 1% faster? For most people here, the answer is no. There's probably something with more business value to do. If you work for one of the cloud providers, the answer is probably yes. So you need to think about it. So as I was saying, the most important things are actually to decide what you even want to do in your performance test. If someone comes to you and goes, can you run a performance test? The most important question to ask is, what do you want to find out? And if they don't know, go find someone who does, or ask if you really have to do it. It's a lot of time spent if you actually don't know what you want because you can't interpret the data. You really need to plan out your tests. Going back to the system tests, you have a microservice or a couple of microservices. What database do you need? In some cases, you want to have it be production-like. In other cases, that's really hard. Maybe you don't. If you're the kind of company where you're making internal software, maybe you don't have any external dependencies. It's just your applications, your databases, it's all fine. We, on the other hand, connect to 30, 40, 50 different third-party systems. And going back to say the example earlier with banking, it's not a third-party system, but they need to talk to their mainframe in COBOL. Do you need to performance test the COBOL, or do you just want to mock that out? You really need some way of monitoring what is happening in detail. A performance test that just tells you, I ran 5,000 requests and on average they took 7.2 seconds. Okay, that's maybe useful information, but if it's not good enough, do you have the data to actually find out why it's not good enough so you can fix it? So understanding the data is really important. And one thing that I believe is who can do this work. So in many companies, this is given to a QA team to do. Maybe they have automation testers who can go write some load generation scripts. That's the easy part. Writing a script to generate load is actually not that hard. Sometimes it's a bit complicated, but the hard part is actually understanding what happened in the application and fixing it. So in my opinion, performance testing is an engineer's job because you need to understand the application. You need to understand how it interacts with other systems. You need to understand the code, and when there's a problem, you're the ones who need to go fix it. Automation QA people can help, but if all they do is run a command that runs a script, you can probably do that yourself. So I personally believe that engineers should be responsible for this because they're the only ones who can actually go and fix things. And the other thing is that you need to redo this over time. Sometimes it's a bit of a one-off. You have a new system, does it perform well? But you should really be doing this more often. When you make a change, you implement a new feature, you should ask yourself, do we need to performance test this? Is it a big enough change we need to care? And sometimes it's just good to do it every now and then because maybe nothing was a performance problem individually, but after 3 months or 6 months of changes, all of those have interacted in a way you didn't think about, and it is now a performance test. And if you have some kind of measurements from last time, you then actually have a better idea of what's good. Because one of the really hard parts of looking at the data is if it's the first time you've done it, what even is good? You don't know. Yeah, so that's all I had to talk about today. Just a bit of an introduction to some of the things in performance testing to go think about. So we've got some time now for questions.
Let's start our Q&A session. Who would like to start first with some insight, some thought?
you. I have a question. If we start this framework, let's say, to test like every next few weeks, so we get the same results or comparable results?
Yeah, so if you want to do every few weeks, that makes sense. Obviously, what you want is a script that runs the performance test. So the one I like is Gatling. It's open source, and you write your test as Java. So I find it easy to use. But if you run it every couple of weeks or however often you want, you can then go, okay, it performed this way before, and a few weeks later it performs this way. And suddenly it's worse. You then know it's something you did in the past few weeks. If you do this once a year, it could have been anything the past year that caused a problem. And so I find it easier to do it more often, but you need to be able to automate the tests, and also you need to have somewhere to do them. So some people have a performance test environment where you can do this. Depending on how you have things set up, a performance test environment, you may not have it permanently. So if you use things like Kubernetes and cloud, it's really easy. You can just deploy it and then turn it off. But in many places, that's quite hard. If you have complicated databases that you need to interact with, making those can be hard, or mainframes or anything. But yeah, I think how often you should do it depends on how fast you change things, how much do you care about performance. So we care a lot because we have fairly high volume and our customers complain about performance. So we need to go investigate how much overhead we add. But how much do you care about it is also part of the thing, because like I said, this takes time to do, and maybe there is something with higher business value like new features or fixing bugs that is more important. So it's kind of up to you how often you want to do it, but it's worth thinking about.
Thank you, James. And now I would like to invite on a stage Paweł Niewęgłowski to present the Community Award.
Thanks.